So I had a question about how do Android async tasks move information from the user interface thread to the background thread and vice versa. So I thought what I would do is walk through a little bit of the source code of async task to illustrate how this works. So here is async task, and you can see here's where it starts. So async task is what's called an abstract class. What does an abstract class mean in Java? You can't instantiate an instance of it without doing something. What is the thing you have to do? What do you have to do with an abstract class? There's something more about an abstract class. It has something else that's, in addition to being abstract, it has some other things in it that are also abstract. What are those? Methods, right. So an abstract class requires you to override at least one of its methods, whatever ones are abstract. And you'll see, which one do you think is abstract for async task? Doing background, right? Because that's basically what you do. So here's some constants that are defined. We have the CPU count, which is the number of available processors. That really should be more core count than CPU count, but whatever. We have the core pool size, which is the CPU count plus 1. We have the max pool size, which is CPU count times 2 plus 1. So assuming that we have 4 cores, that would be 5 and 9. Keep alive is set to 1. We make ourselves a thread factory that has a count, which is an atomic integer. And you can see that whenever a new thread is made, we're going to put the name async task number, and then we're going to get and increment that count so that we keep each thread that we create, or each thread that's created on our behalf, will have a different name. So you see how that gets used. That's a useful thing to know about. There's something called a blocking queue, and we have a pool work queue. This is going to be used to queue up the async task instances if there are more of them than there are threads to run them in a pool of threads. So we have 128 runnables, which is our pool work queue. We have our thread pool executor, which we actually looked at this before. Thread pool executor is a new thread pool executor for core pool size, which if you recall, I think was, let's say it was 5. Max pool size, which I think we decided was 9 if there were 4 cores. Keep alive is 1. That means there's 1 second. What this is saying is we'll create some extra threads up to max pool size threads, and when those threads have not been active for more than a second, they get shut down, but we always keep core pool size number of threads in the pool. Yes? Sure. Question is, how do we calculate core pool size and max pool size? So as you can see, core pool size is simply CPU count plus 1, whatever CPU count was, right? So CPU count is a count of the number of cores that the virtual machine knows about. So let's say, for sake of argument, that there are 4 of them. Now, that's whatever runtime.getRuntime.available processors returns. That's a virtual machine level method that keeps track of that information. So let's say, for sake of argument, there's 4 cores, like you might have on a phone these days. So core pool size is CPU count plus 1, so that would be 5 if there were 4 cores, whereas max pool size would be CPU count times 2, 8 plus 1, 9. Does that make sense? Well, the person who wrote this code added that, and I'm assuming that they did that just because they figured that, if you have 4 cores, maybe somebody will be blocked, and so we want to have an extra one left over. But I don't know if there was any particularly deep reasoning behind it. If you take a look at the code, you'll see that earlier versions of Android did it in a slightly different way, but this is what it's doing now. Okay, so we have a thread pool executor. We also have this thing called a serial executor. We'll get to that in a second. There's some messages we're going to pass back and forth between background thread and foreground thread. We just give them unique names, post result, post progress. We have this thing called the default executor, which is the serial executor. There's this thing called internal handler. Internal handler is important here. Internal handler is going to be used as a way to pass things back and forth from the background thread to the foreground thread. And the thing to note is that the internal handler here is static. And that means it's going to have an affinity, or it's going to be connected to the user interface thread, because it's going to be created in the context of the user interface thread, because that's where statics get created. There's also some other really interesting fields here, mWorker and mFuture. And you'll see that mFuture is a future task, which is a built-in Java class that's pretty cool. And then we have this thing called worker runnable, which is defined later. And that's just a way to move stuff around when you make a new instance of an async task. We keep track of the status, pending. We keep track of things as to whether the task has been canceled and whether the task was ever invoked in the first place, because you can always create an instance of an async task but not actually execute it. So we keep some atomic booleans to make sure that we can atomically check these fields and set them if we need to. Here's the serial executor. Serial executor is what's used to run things by default in a background thread, one and only background thread. This allows us to be able to do in a background thread, but only have one thing happening at a time in that background thread. So by default, if you do nothing else, if you don't have execute on executor and you don't give it a thread pool that has more than one item in it, more than one thread, then what will happen is that there'll be a background thread that's created, as I'll show you here, and all async tasks will run serially in that background thread. What's the reason for executing things serially in a background thread? Why does it do that? Why does async task have that as the default behavior? Bruce. So you don't block the UI thread, so you can do things like do a network call. Remember, network calls can't run in the UI thread, but they can run in the background thread. So that explains why we have a background thread. But why do we only have one background thread? Joe. Right, so that users can be pretty blissfully unaware of synchronization. So the way it works is by default, it'll allow you to run things in the background, but just one thing at a time, so that you don't end up with race conditions if you're not smart about having locks in your code. Now, so what's the downside with that? The upside is it's easier on you, but what's the downside? What's that? Only one thread. So you're not really leveraging the multi-core features very effectively, which is why you can override that using the strategy-like mechanism to pass in a different executor to run async tasks in parallel. But this is the default. So as you can see here, we talked about this before. Serial executor implements executor, so that means it has an execute method. That execute method is going to take a runnable, and it's going to go ahead and enqueue that runnable such that its run method will get called back, which will get called back in a background thread, and then it's going to go ahead and schedule next. So this is just ensuring that there's only one thread running at a time, and if it is running, it's running in the background. And the way this works is we keep track of a deck of tasks. Honestly, not sure why they use a deck. They probably could have got away with a simpler data structure. But be that as it may, what this thing does is when you execute something like this, it will put it onto the queue. And if there's nothing on the queue, it'll call schedule next. Schedule next will pull something off the queue using poll. What is the semantics of poll? If you call poll on a Java collection framework instance, what does poll do? What would you expect it to do given the name poll? Would you expect it to block? Would you expect it to not block? Does not block. So what poll does, take is the method that blocks. Take will atomically wait until an item is available and then remove it, but it'll block if it's not there. Poll, in contrast, will atomically try to remove an object from the queue, or the deck in this case, and if it's not there, then it returns null. If it is there, it'll get back something that's non-null, but it doesn't block. We don't want it to block. So it gets back the object, and it goes ahead and executes it. And notice how it executes it in the thread pool executor, but this little protocol ensures there's only ever one thing running in the background at a time. All right, here's status. Status keeps track of the status, or the state of the async task, which can be pending, which means it's been created but not yet executed, running, which means the task is actually running in the background, or finished, which means it's done. And you'll see that there's some sanity checking in various places to do different things based on the status. Here's here's a method called getHandler, and you can see this is synchronized by the class. So this means that it can be called in different threads, and what it'll do is it will go ahead and initialize this sHandler to a new instance the first time it gets called. So the first time getHandler gets called, it's going to go ahead and initialize the handler. This is basically the singleton pattern, or a variant of the singleton pattern here. Okay, by default, we set the executor to whatever's passed here. This is a very funky method, by the way. Notice how it's marked as hidden. And what that means is even though it's defined as public, you can't access it. It's not actually visible. Very strange use of annotations to modify the semantics of the methods. Here's the constructor for an async task. So whenever you say, new async task, this is what's going to get called. And what it does some really interesting things here. It makes a new worker runnable, and we'll look to see what a worker runnable is in a second, and it stashes that away. And the worker runnable, this is what's called an anonymous inner class. And we're defining an anonymous instance of a subclass, of an anonymous subclass of worker runnable that has a call method defined. And when this thing gets called, it's going to say, hey, this task was invoked. And notice that when it's called, this is now going to run in the background. And it's going to set the priority of the thread to the background thread priority. So that what that means by default is that a background thread running do in background runs at a lower priority than the UI thread. So we're giving preference to the UI thread by default. If you don't like that, you can override this in the do in background call. And so keep in mind that this call method is going to run in a background thread in the thread pool that's running, the thread pool executor, for example. And it's going to call do in background, which is the hook method that gets called. This comes back to, I think, Bruce's earlier question. So do in background gets called in the background thread. We pass the parameters that were set to that. And when it's done, it's going to call post result. And we'll see in a second when we look at post result that post result is going to send the result from the background thread to the user interface thread. It's going to send it back by passing a message. We'll see what that does in a second. So this gets called in the background. Then we also make ourselves something called future task. And notice how future task is given an M worker. It's given the M worker as a parameter. So future task is created with the M worker. And when its done method gets called back, it will basically try to get the result, and it'll post the result if nothing was invoked. It handles a whole bunch of different exceptions here in various kinds of ways. So we'll take a look at those things in a second. All right. First, let's, well, we'll just keep going. So here's post result if not invoked. If the task was never invoked, we're going to post a default result. In contrast, post result is what gets called back after do in background returns, right? So when do in background is done, post result gets called back. So here's what do in background, or here's how this gets called. You can see up here, the call method calls do in background. It takes the result, which is in the background, gives it to post result, and then post result goes ahead and does the following. It creates a message, which is a post result message, and it's going to give that message an argument, which is an async task result, which is basically the result. And it's going to go ahead and it's going to send that message to the target. So notice what it's doing. It's saying getHandler. So getHandler is going to give it back the reference to the static handler object, which has an affinity with the UI thread, so it's bound to the UI thread. We're going to make a message that says, I'm the post result message with this async task result, which is the result that came back from do in background. And then it says, hey, message, send yourself to the target. So what that's going to do is it's going to go ahead and stick it on the message queue of the handler that's got an affinity to the UI thread. And that's how the UI thread gets called back. And we'll see what that does in a second. A little bit of magic. That's actually using the Hammer framework, which we haven't talked about as much, but that's what's being used. All right, here's where the hook methods are defined. So you can see do in background is an abstract hook method, which means you have to override it. Otherwise, nothing happens. You can see that, or otherwise you can't instantiate the instance of async task. Here's on pre-execute. You can see that on pre-execute is given a body that by default does nothing. So you don't have to override on pre-execute. It's just a no-op by default. Here's on post-execute, same thing. It's given a body such that by default on post-execute does nothing. Same thing for on progress update. Same idea. No body, or it's a no-op, it has a body that does nothing. On canceled, same thing, etc. Oh, here's is canceled. Is canceled simply checks to see whether or not this computation has ever been canceled. Just returns a get method on the Boolean, so it's atomic. Here's the cancel method. As you can see, when cancel is called, it goes ahead and it sets mCanceled to true. Atomically, mCanceled is an atomic Boolean, so we can set it to true. And then mFuture.cancel, that says to the future, shut yourself down. Well, that was defined a little earlier. OK. Here's the get method, simply returns the future's result. Here's the timeout version of that. Here is the execute method. So this is kind of cool. This is the method if you just use an async task in its simplest form. You say, new async task, blah, blah, blah. And then you say, let's say you say, async equal new async task, blah, blah, blah. Then you say async dot execute, given any parameters that you might have. That's the method that gets called. As you can see, what it does is it calls execute on executor with the default executor, which will always be the single threaded version, the serial executor. So by default, or always, execute runs things one at a time in a background thread. So that's what that does. A much more interesting method is execute on executor. You can see what execute on executor does is much more interesting. First thing it does is, of course, it's also passed an executor along with the params. It first checks to see whether or not we're in the right state. So if the status is not pending, then something's gone wrong because either it's running and we're trying to execute an async task more than once, which is against the rules, or it's already finished running and you can't execute an async task more than once, so that'll throw exceptions. Otherwise, it sets the status to running. It calls the on pre-execute method. Remember, execute an executor should be called in the UI thread. So it'll call on pre-execute in the UI thread. It then goes ahead and sets the parameters for mWorker to what was passed in up here. And then it says, hey, executor instance, which is this guy right there, go ahead and execute mFuture. And what that'll do is that goes ahead, remember what execute does is it schedules this thing to be run in a background thread in the executor that you have at that point, which in this case could be a thread pool executor, or it might be the serial executor, or it might be an executor that you implemented, which is the way it would have been for your assignment, or will be for your assignment. And then it returns this. So it always returns the object so you can chain these things together. This is just a convenience method, not really very useful. Here's publish progress. Remember, publish progress is a method you can call from the background, do in background method in a background thread, and it's going to take the values and pass them to the UI thread. And here's what it does. If it hasn't been canceled, then it goes ahead and gets the handler to the internal handler, which has got an affinity with the UI thread, gets a message, makes a new async task result object with the values that you want to send to the UI thread, and then sends that message to the internal handler, which has an affinity with the UI thread. We'll see how that all gets processed here in a second. Finish is just an internal method. It's private, and it just checks to see what happens if you were canceled. It calls the onCanceled return value or hook method. Otherwise, it calls onPostExecute, and it sets the status to finished. Here's the internal handler. I keep talking about the internal handler. An internal handler is a handler, and what it does is when it's created, it'll go ahead and set its affinity with the main looper. That just means with the UI thread. And then its handle message method will get called back. And this is the method that gets called back when you do a send to target. When the send to target method is called in a background thread, the Android Hammer framework will arrange to call the handle message hook method with the message that you created in the background thread in the UI thread. So this handle message method is called back in the UI thread. It scoops down here, pulls out the object field of the message, which it casts to an async task result, because that's how we created it. And then it'll take a look and see what kind of a message it was. Was it a post result, which is what happens when we're finished, when do in background is done? Was it a post progress result, which happens when we call publish progress? There are two different message types. If it was a post result, we basically are going to say, finish yourself up, passing in the result. If it's a post progress message, we call the on progress update hook method on the async task with the data. And so this will end up resulting in that callback. The call to finish, if you'll recall, simply either calls on canceled or on post execute. So this method here is just how we get stuff back. I think that was Bruce's original question, was how do we get the results back from the UI thread to from the background thread to the UI thread? It's by passing a message from the background thread, which gets queued up in the handler, which is got an affinity with the UI thread, such that when the handle message method gets called back on the handler object in the UI thread, it cracks open the message and then finishes dispatching things. So this is a really cool example of a concurrent template method pattern, which is kind of neat. And then the last couple pieces of the puzzle here is we have this thing called worker runnable, which is just a class that's going to keep track of the parameters we want to pass. And then we have async task result, which is just a way that we pass back the results associated with a particular task. So that's the implementation of async task in a nutshell. Not a whole lot of code by programming standards. What is it? So looks like we've got, let's say, what is it? 676 lines of code. So it's not a very big class. But it does some really, really cool things. And the things that make it mostly cool, or particularly cool, is the fact that it's got this ability to both subclass and override these hook methods, like do in background, on pre-execute, on post-execute, and so on, and then have the framework call those methods back in different thread contexts. That's the magic of this thing. So we subclass it, but it knows internally how to get the callbacks to take place in the right thread context. And when it has a call that's done in one context, but it needs to have the result in a different thread context, it uses the Hammer framework of Android to pass messages from one thread context to execute in a different thread context. So that's the beauty and the power of async task.